Hello everyone, welcome back to the course Introduction to Multi-Agent Systems. I am your course instructor Dr. Twinkle Tripathi from the Electrical Engineering Department of IIT Kanpur. In today's lecture, we will talk about some basic mathematical preliminaries which will help us to do the analysis of multi-agent systems. So let us get started with them. These are some of the notations that we will be using throughout the course. Now we need not go over all of them now itself. Whenever we hit upon something, I'll explain what it means. One of the first basic structures in linear algebra that we'll talk about is a group. So a group is simply a set which has to be of course non-empty for it to be meaningful. Now the set G is equipped with a binary operator denoted as addition. Note that it is represented as addition, but it could mean any other operator for that matter. Additionally, this set, the set of elements along with the operator, have to satisfy a few properties for the set to become a group. Now the first property that it has to satisfy is the closure property. In the closure property, we take any two elements in G and operate them under the given operation, then the output of it has to lie in this set itself. The second property is associativity, in which the order in which we perform the operation doesn't really matter. For example, if we have three elements here and we take x plus y plus z, now it's exactly the same as doing first x plus y and then operating it with z, known as the associativity. Now the third property is about the existence of a unique element E. Now what is this unique element E? It's known as the identity element. Why is it the identity element? Is because whenever E is operated with an element x, then our output is equal to x itself. Similarly, there exists another unique element which is known as the inverse element. Now the inverse element is unique only with respect to the given element. For example, if I start with any element x belonging to G, then the property of the inverse is that, let me denote the inverse as x bar, then x operated with x bar gives me back the identity element. Any set which satisfies these properties becomes a group. Now there is an additional property which we can associate with the set, that is the property of commutativity, meaning if I do x plus y and it is exactly the same as changing the order of the elements, then the operation becomes commutative and the group becomes an abelian group. So let us see some examples of a group. Z is a set of integers that we have, and here we denote the plus sign as the standard addition operation. Now let's see how does it become a group. To start with, whenever we add any two integers, obviously it is still an integer, meaning it satisfies the closure property. The second one is the associativity. Of course, if I add two integers, this holds, meaning the associativity also holds. And what is the unique identity element here? That is obviously the element 0. Any integer when added with the element 0 gives me back the same integer itself, and the inverse of an integer, which is minus of x, gives me back 0. So meaning and minus x always belongs to the set of integers. Hence I know that the set of integers along with the addition operation becomes a group. Is it an abelian group? In this case, yes, it is an abelian group as well. Now similarly, we can take the set of n cross n matrices with the addition operation. So please try it out for yourself and see whether the set M which is given to us becomes a group or not. And there are similarly some more questions which you can try, which is what happens when we change now the addition operation to a multiplication operation? Does the set of integers along with multiplication still remain a group? Similarly for the set of matrices. Please try to solve these for yourself. Now, let us look at the next structure in linear algebra, which is that of a ring. So, what is a ring? A ring similarly is a non-empty set denoted by R. Now, unlike the group, it is equipped with two operations, which we denote as the addition and the multiplication. Again, these are just representations and could actually mean any operation. R, along with these two operations, must satisfy a few properties so that the non-empty set is a ring. The first condition is that under the operation of addition, R must be an abelian group and with the existence of the identity element as E. Of course, we have the now the next operation is the multiplication operation. For the multiplication operation, the first property that must hold is the closure property. Let's write it here. If we multiply any two elements within the set, the product of it must remain in the set itself. The second property is associativity. So, with respect to multiplication, associativity should also hold. And the third point is the existence of a unique element 1 such that 1 when multiplied with x should give us back x itself for every element in the ring. And the third property is the distributivity property, where the distributive property holds in this manner. Suppose we take the addition and multiply it with another element z, then we see that multiplication distributes over the addition, meaning it should become x times z plus y times z, as shown here. Additionally, if the operation of multiplication also commutes, then R becomes a commutative ring. Let us take a look at a few examples. The first example is that of the set of integers along with the operations of multiplication and addition. Now, it can be shown in exactly the same way that we did for the case of a group, that Z is actually a ring with respect to these two operations. Similarly, the set of matrices, it can be again very easily shown that this also remains a ring, becomes a ring. Let us now look at the third structure, which is of a lot of importance to us. We will keep talking about fields, and the fourth structure will be the vector spaces. So, these two structures are something that we'll keep talking about. So, let us now discuss what exactly is a field. A field is a non-empty set F. Again, it is equipped with two operations. The first one is addition and the second is multiplication. Now, the set F along with these two operations must now satisfy a few properties. So, what are those properties? The first is the existence of the unique elements E and 1. What is 1? 1 is the multiplicative identity, meaning if I take any element belonging to the set F and I operate it with 1, I should get back the element itself. Similarly, we have the additive identity again for any element belonging to the the field. For any element belonging to the field, x when added with the identity element is x itself. So, these two identity elements must exist in a field. Then F should also be an abelian group with respect to the addition operation. Now, F should be an abelian group under the multiplication itself with one small condition, which is that we need to subtract or take the element additive identity out of the set. Then F minus E must be an abelian group under the multiplication operation. So, these are the properties. Let us now quickly see some examples of fields. Now, the set of rational numbers Q under the the set of rational numbers under the operation of addition and multiplication is a field, because obviously it can be seen that they satisfy all of the properties that we need to have. So, I am omitting so in general in a question, when somebody asks us whether something is a group or a ring or a field, what do we need to do? We need to go and check all of the basic properties which we discussed in the beginning: closure, associativity, then the existence of the unique elements. So, we have only one unique element in the case of a group, which is the additive identity E. And then we have the multiplicative identity as well in the case of a ring and a field. These are the basic properties which the set has to satisfy. Now, for it to be a field, F also has to be abelian, meaning whenever I do this, it has to be equal to this as well. Similarly, every element other than the identity element must also satisfy the commutative property with respect to the multiplication operation, meaning this. So, all that we need to do is check whether a set satisfies these properties or not. If it satisfies all of these properties, then it becomes a field. So, again it can be very easily seen that the set of rational numbers and the set of real numbers actually form fields under the standard operations of addition and multiplication. Now, interestingly, the set of integers does not form a field. Why does it not form a field? There is something that becomes missing there. Let us see. Suppose I take an element x and multiply it under the multiplication operation. Now, what should this entry be so that I get back the multiplicative identity, which I denote with 1. Now, what should this element be? It is 1 by x. Note that 1 by x may not belong to the set of integers. Hence, the multiplicative inverse of x is not a part of the set, meaning the set Z is not a field. Okay. Now, we will talk about the last structure in linear algebra, which is a very important structure for us, which is something that we will keep talking about at least for the next few lectures, or we will keep using some form of it. So, what exactly is a vector space? Now, the vector space is actually a set of vectors which are generally defined over a field F. Okay. Now, we talk about the last structure of linear algebra, which is perhaps one of the most important structure that we will keep using as well, at least for the next few lectures, which is a vector space. So, what is a vector space? A vector space is simply a set of vectors which are generally defined over a field F. And so, V together with F. Now, we know that whenever we have a field, we will need to have some operations, but now the vector space as well has, the set of vectors also have some operations. Let me write this slightly better. which is the operation of addition and multiplication. Now, unlike the elements in a field, the set of vectors are added and multiplied slightly differently. So, let us understand what do we mean by that. So, in a vector space, generally whenever we talk about addition, we refer to the addition of vectors. But whenever we talk about multiplication, we talk about the multiplication of a vector with a scalar. So, we call it a scalar multiplication. Now, what is a vector and what is a scalar? Let us first start by defining that. Any element which belongs to V, the vector space, is a vector. Any element which belongs to my field is a scalar. So, this is a terminology that we will keep using throughout the next few lectures and perhaps even later in the course. Okay. So, now let us see what are the properties that vector addition and scalar multiplication has to satisfy. Now, the first property of vector addition is the existence of the additive identity 0. What does the additive identity do? Again, same thing that we have been talking about for the scalars, which is u when added with the additive identity gives me back u itself, and this should hold for every element in the vector space. The second property is the commutativity of addition, meaning u plus v is equal to v plus u. Then we have the associativity property, and we also have the additive inverse. What does the additive inverse do? As before, let us say we take an element u and add it with its additive inverse, we must get back the additive identity. So, the vector addition has to satisfy these few properties, so that for it to be able to called a vector space. But there are few properties that the multiplication also has to satisfy. They are, the first is the existence of a scalar identity, meaning now there must exist some element which now sits in the field. So, we have two spaces, let me call this V and F. So, whenever I am adding, I am always taking these elements into account, but whenever I am doing a multiplication, I take an element and multiply it with an element here. Okay. Meaning this one should belong to my field, and this when multiplied with the scalar u gives me u itself, and this becomes the multiplicative identity. The second property is associativity, which is as defined before. It takes this form. The third property is the distributivity property, wherein about the distributivity of multiplication with respect to the addition operation, which means that if now I multiply a scalar with the addition of two vectors, then it should be the same as multiplying the scalar first with both of the vectors and then adding them up together. So, this is the distributivity property. Now, any set V which satisfies these properties, of course, there has to exist a field over which a vector space is defined. So, a vector space is incomplete without the existence of a field. So, any set which satisfies these properties becomes a vector space. So, this is also a second form of distributivity, which is again defined very similarly. Okay. Now, let us quickly see some simple examples of a vector space. Now, let us consider V as being equal to R2, which is the set of real numbers in R2, and I define my field as a set of real numbers, meaning again I have two of my sets. This is R2, this is R, Now it's very easy to check that whenever I'm taking any two elements here and adding them up, obviously it belongs to R2 itself, and we know that R2 has the origin, which will serve as the additive identity, and it can satisfy associativity as well. So we know that vector addition holds. Oh, sorry, this should be R. So this is my field, this is my vector space. Now the next thing that we check is the scalar multiplication. Now in the scalar multiplication, I take some element here, meaning let me take now some real number C and multiply it with some element in R2 like this. Now obviously this satisfies the closure properties because this belongs to R2. And we can easily check that 1 will serve as the multiplicative identity here. So it satisfies all the properties of scalar multiplication as well. This holds. This also holds. The next property is distributivity, which again can be very easily checked. Let's see that quickly. This is obviously the same as similarly, if I write, I know that it is the same as this. So the third category, which is distributivity, also holds. WRT is something that is commonly written for with respect to. Hence, I know that the set R2 over the field R is a vector space. So there's another example that we can take, which is the set of all polynomials in some variable t of degree n. Now please try to answer this question for yourself and do the calculations and see whether the set of all polynomials of degree n will satisfy the properties of a vector space or not. So we'll pause the lecture here today. This is some assignment that all of you should try, and in the next lecture we'll talk about some more elements of some aspects of linear algebra, especially pertaining to those of subspaces. Thank you.